So we saw a way of putting data into lists in Python and making a plot, seeing how things look. Now we'll start on the path of finding a mathematical equation, a mathematical function that a set of data seems consistent with. That's what we do, confront math with real data. So we'll come into Collaboratory, new notebook, give it a name right away, so don't forget this time. First time to fit a mathematical equation that will describe some data. And save early and often. So remember the cell with a little place symbol, that's a code cell. If you want a text cell up above it, you can double click in it and say, here's some data. Shift enter, take me to the code cell. Okay, now my screen recorder will only let me record 15 minutes. So to save recording time, I'm going to stop recording, put in the numbers, and then start recording again. So then you can see the numbers and take your time to put it into your own notebook. Okay, so here I put in some XY data for a pretend projectile. I can put in uncertainties too. I can use the trick. Uncertainty Y equals, if the uncertainty is the same, let's say the smallest marking on my stick is 0.1, and multiply that by the number of data points. I don't want to count them, so I will use a function that will count for me, length of Y. And that should do everything pretty good. Just to check, I will print all these, print X, Y, uncertainty of Y. And they'll look okay. Looks like everything has 11 data points. Okay, cool. It's good to make a quick graph of the data before you do anything else. So what are the steps? I'm going to put a code up here. Before I was a little sloppy. When you're importing things like the plotting routines, it's considered proper to do all of that at the beginning. So import matplot lib.pyplot and give the nickname plt. And I can just run that by itself, and now it's there. So now I can add a code plot down here. You can look back or try to remember, look it up. Give you a second. plt.error bar. Give it the horizontal variable, vertical variable. Specify y error equals whatever the size of the error bar is. I think this time I'll use the format I've used before, KO, so the plot is little circles. And then cap size tells you the size of the bars on the error bars. I think 0.4 is what I used before. Let's try that. Maybe I was supposed to put FMT equals here. And there it is. Little dots with little error bars. And we want to know what is the equation of the ideal parabola that would go through these experimental points. Because experimental points, they have some uncertainty. That's why the error bars are there. So they may not be exactly on the parabola. So there is a tool that lets us calculate functions. It's similar to the loop tool that we used in Python, but it's set up a little different. So I'll set up another code cell down here. Put a blank line here. And here's what we want to do. It's the equation for a parabola. I'm going to put a tab here. This is similar to a loop. It's something that we want to be able to do again and over differently from a loop. So it's something special. So I'm going to put a tab here. The thing that's going to be calculated in this set of code in this function is a parabola. It's a parabola a times x squared, remember 2 asterisks does a power, plus b times x plus c. That's a generic parabola. So there's 2 more things we have to do before our code can use this equation to calculate parabolas for whatever x, a, b, and c we want. Because we don't want to have to type this out with different numbers all the time. We just want to be able to refer to this equation and say, hey, use these equations. First thing we have to do is, in the line before, unindented, we have to say, well, we are defining something. We're defining an equation, what's called a function. So define, say, para, for parabola. And in parentheses, we put the numbers, we put the arguments. In other words, we have to put the fact that there's going to be an x, a, b, and a c. And for now, we're just going to call it x, a, b, c. In other words, at some other point in the code, we're going to use this word para. And the computer is going to say, okay, I'm going to look to see where para is defined, and the numbers that are inside the parentheses I will apply to this definition. So these are place markers. The first number will become x, the second number will become a, third number will be b, the fourth number will be c. Have to have a colon here, just like we did with the loop. So that's one thing. We have to tell the computer we're defining some special equation that it can use again and again. The equation itself could be several lines. It's indented. And at the end of the line, I need one more indented line here. And that is the part that says, okay, so what exactly is the number that's going to be output from this? It might not be y. There may be some more complicated thing being calculated, but in this case it's y. So we use the magic phrase return y. And that's what's going to tell the computer you do this calculation and then put y back where you're seeing this word para, because you've done the calculation and you're going to put this number y somewhere. You can hit enter a couple times, backspace, and then I'm going to just do a test of this. Print para, so now I'm saying I'm invoking this magic function para, parentheses. Now the 4 things that go in here will correspond to the 4 things in the definition, a, x, a, b, and c. So maybe I want to do this at x equals 1. I want to set a to be equal to 2. I want b to equal, let's say, -4. And I want c to be equal to 10. So this is going to calculate a parabola with x equals 1, a equals 2, b equals -4, c equals 10. What do you think will happen? If you do the math, 1 squared times 2 plus 2 is 2, and then -4 times 1 should be -2 plus 10. I'm coming up with 8. And there it is. So here's a cool way you can use these functions. I'm going to go back up here and copy this line that plotted the graph with error bars. So I'm going to do it again. And I'm going to paste it into this new code cell. And on top of that, I'm going to put a plot of this parabola. I forgot to give it a format, so it's just something we can't see. So I'm going to make these, let's say, inside the quotation marks, G for green and X for X's. Okay, there's one other thing I can do in case I forget what's what. First plot, I can label it, say this is data. The second plot, I can label it, say this is some theoretical equation. And then I can add a new line, undent it, so it happens after all the plotting, and say plt.legend. And then that will give me a key. Right, okay, so the way I did this was not ideal. We'll do it a better way later, but you can see this is not a very good graph. And the equation is not doing well. How do you fix it? Well, you try to do different values. So for instance, maybe my value of A looks like it's curving a little too much, so I'm just going to do 0.2. Negative 0.2, and just try that. Well, that's a little much, but maybe, I don't know, maybe B is too big. Maybe that should be 2. Well, it's getting closer. My legend is still a little messed up. We'll do that in a better way. But you could, in principle, play with this and change these numbers A, B, and C and get the X's to be as close to being on top of the dots as possible. Looks like maybe B just needs just a little bit smaller, maybe 1.5. Well, that was a little too much. We were better off with 2. So you can try this for a little bit. Try and do as well as you can to get the theory on top of the data. But obviously this is not the ideal way to do it. So in the next video we will look at the template that we will give you that will show you how to use another Python set of code, another Python library set of functions that other people have written. And it will do the work of finding the equation that comes closest to making it work. That would get the x's as close to the dots as possible, given the fact that the dots have some error, so they may not fit the line, the curve, the function absolutely perfectly. One of the wonders of doing recording this way is I can fix something and then just tack it on in the last minute I've got left. I had forgotten that the way to do this with lists is first I have to make an empty list. That's what this does. Square brackets with nothing in it. And then in the loop I append to the list for each x, I append to it the calculation of the parabola. So now I actually have another list, which is the fits. Then I plot x in that second list, and now everything looks good. Except you can tweak the numbers in here to try and get it a little bit better. So here I just did one last tweak, and it got a little bit better. Okay, but we'll let the computer do the hard work. This is really the end now.